what's up, guys? Welcome to day 50. Today you guys took a good, tough test. Nice job staying focused, working hard, remembering your rules. I'm not necessarily looking forward to doing grading, but I'm looking forward to seeing your guys' great work. So, today I'm going to introduce a topic called related rates. These are often problems in word problem form that can be very difficult. But to make them easier, we're really going to focus on a process that's going to allow us to solve this correctly every time. So here's what I want you to do. Whenever you come to a related rates problem, we're going to follow these simple steps. Okay, step 1. Make a no list. You're going to be given a lot of information, and what we want to do is we want to make a list of things that we know. What I want you to be careful of is be careful of values versus rates. So distinguish rates from values. Rates are going to be derivatives, so when we put them in our no list, we want to indicate that they are going to be derivatives. Values are not derivatives, and we should list them as constants. Okay, so we want to make a no list. The second thing we want to do is make a need list. Need is what we're ultimately trying to answer in the question. Most of the time, most questions, there's only one thing that you need, right? And that's our final answer. This is almost always a rate, but I'm not going to say always a rate because it's hard to make an always statement. There might be times when we're finding a value, but almost always we are finding, this is usually a rate. The other thing we want to do after we make our no and need list, is there anything else that's not explicitly stated that we do know, that we could find out? Okay, so we'll take a look at that as they come. Those are usually on trickier problems. Step 3, we need to find an equation that when we do the derivative of this equation, our need will appear. Find an equation that will yield the need. After we find that equation, we want to derive. And when we derive, we do this like an implicit differentiation. Like every value is the y. Remember how we always tacked on dy dx whenever we did a derivative of y? We're going to do that now, but for every variable. Tack on d whatever it is dt. Okay? Then lastly, we want to solve for the unknown. Solve for the need. Okay. Those are the steps that we're going to go through, and these steps will work every time as long as we're careful and as long as we set this thing up. Just as a side note, I really like these problems because they involve lots of different areas of math. Oftentimes this is a great intercept between geometry and calculus. And sometimes it can be an intercept of physics and calculus, but related rates have a lot of fun stuff with them. So without further ado, I'm going to give you an example here that we're going to break down. Okay, so here's the example. When I'm finished writing it, just pause the video so you can catch up and make sure you have the problem written down. Okay, so again, pause to get that all written down. Okay, so here's the problem. A circle is expanding. The radius is increasing at a rate of 4 centimeters per second. What is the rate of change of the area of the circle at the instant the radius is 10 centimeters? Okay, so there's a lot going on here, so let's go back to our steps. The first thing that we want to do is make a know list. Okay, so things we know, we're dealing with a circle, okay, and that circle is getting bigger. If that circle is getting bigger, that means its radius needs to be getting bigger, and its area needs to be getting bigger, and its circumference would be getting bigger. All of those things are happening, okay? Now what we want to do is we want to take these numbers that we have numbers 4 and number 10, and figure out what they are, to determine if it's a rate or a value. Right? Rates are easy to tell because they're going to be a unit divided by seconds, right? So when we take a look here, it says the radius is increasing at a rate of 4 centimeters per second. Okay, that doesn't mean the radius is 4. It means the radius is increasing at a rate of 4 centimeters per second. So what that means is the rate of change of r is 4. So the way we write that down, okay, this is a rate, and rates are derivatives. It's the derivative of the radius with respect to time. So what I write in my know column is dr dt equals 4. I usually don't like to put my units in here. I'll just consider units at the very end. So dr dt is 4. The radius isn't 4. The radius is changing at a rate of 4. So my rates, right, since it's radius is dr dt. If it was circumference, I would call it the rate of change of circumference. I'd call it dc dt. Okay? If it was the rate of change of volume, I'd say dv dt. If it was the rate of change of length, I'd say dl dt. Okay? It just needs to be in derivative form. The other number here I have is 10 centimeters, and that 10 centimeters is the instantaneous value of the radius. So the other thing I can add to my know column is that r equals 10. R equals 10 in this problem when I'm evaluating this thing out. Okay, those are the only two things that I know right off the bat. Now I need to look at what I need. So look for the question word, and then that'll usually help you. So the question word is what? What is the rate of change of the area? So what I need here is rate of change of area. I don't need the area, right? That would be a very 8th grade question. The area of the circle when the radius is 10 would be 100 pi. That is not the level of question we're dealing with here. What I want to know is how quickly is that area changing? What is the rate of change of that area at that exact instant? So what I need here is a rate. So what I need here is dA dt. So I need dA dt. After my know and after my need, I want to find an equation. I want to find an equation related to the shape that I'm dealing with, right, or the scenario that I'm dealing with, that when I do the derivative, I'll get dA dt, right? I need area to come out here. Now, we should know two equations with circles. We know an area equation and we know a circumference equation. Obviously, the equation we want here is area, so when we derive it, we get dA dt, right? If I asked what's the rate of change of the circumference of the circle, then I'd want to use the circumference equation for a circle. It is expected on the AP test that you know the equation for the area of a circle. So the equation here is A equals pi r squared. So what I have here is A and R are my variables, pi is a constant. So when I go through and do my derivative, right, step 4 is to do the derivative. When I do the derivative, I'm going to remember that pi is just a constant. It's just like a coefficient. Okay? So what I'm going to do here is I need to do the derivative of this equation. But every time I do a derivative of a or r or any other variable, I do the derivative as normal and tack on d, whatever the variable is, dt. Okay? Just treat it just like we treated y's when we did implicit differentiation. So when I do the derivative of a, right? Notice I never plug, I'm not going to plug things into my equation right now. I'm not going to plug things in until I get my derivative, unless there was something else I needed in my no column. So I'm just going to do the derivative of the left side of the equation and the derivative of the right side of the equation. So the derivative of a, starting there, the derivative of a is 1 times dA dt, or I'll just write dA dt. Okay, now the derivative of pi r squared is going to be, it's just a power rule here, nothing fancy. My derivative of pi r squared would be 2 pi r, but I need to multiply by dr dt. Now, after I've done my derivative, the last thing I want to do is solve. In this case, I want to solve for dA dt. So what I want to do is I want to plug in everything I know. Hopefully the only unknown is dA dt. That's the one I need. Hopefully everything else is known, and I'll be able to solve this thing, and then I'll consider units at the end. So dA dt here is unknown, which is okay because it's in my need column. There shouldn't be anything to plug in for it because that's what we're trying to solve. 2 and pi are constants, so there's nothing to plug in there. What do I plug in for r? Well, I look back to my no column and I say r equals 10, so I'm going to plug that in here. And then what goes in for dr dt? Well, that would be up here, 4. Then I crunch all those numbers together. 2 times 10 is 20, 20 times 4 is 40, or sorry, 20 times 4 is 80. So I end up with 80 pi. Now I need to consider the units. Well, it'll be area units divided by time units. Right? Area is always square units. In this case, the problem deals with centimeters, right? So it'll be square centimeters per time unit. The time unit I know from the problem is seconds. So that means if my radius is growing at a rate of 4 centimeters per second, then when the radius is 10, the area of the circle is increasing. We know it's increasing because it's a positive number by 80 pi centimeters squared per second. Okay? So that's the kind of problems that we'll see. That may seem hard right now, but that will be a very simple problem for us eventually. Okay? Let me show you another problem. A rectangle is changing dimensions. The length is increasing by 3 centimeters per second, and the width is decreasing by 2 centimeters per second. What is the rate of change of the area of the rectangle when the length equals 10 centimeters and width equals 6 centimeters. Okay, so again, pause it here quick, copy on this problem into your notes. Okay, so we have a different problem here. Now we're dealing with a rectangle that is changing dimensions. The length is increasing by 3 centimeters per second. The width is decreasing by 2 centimeters per second. What is the rate of change of the area of the rectangle? Now, this one's a little bit tougher. Right? It was pretty easy to see that our area would be getting bigger on our circle because the radius was getting bigger. It's a little bit, we're unsure right now looking at this. Is this rectangle's area going to be getting bigger or smaller? Well, it's kind of hard to tell because one dimension is increasing and one dimension is decreasing. Okay? So it's not super clear. Maybe the area is staying constant. Maybe the area is 0. The rate of change of the area is 0. Or maybe the area is getting bigger, or maybe the area is getting smaller. We just don't really know until we do the problem. Right? We can try and guess, but we're going to need to do the problem anyways. So let's make a list of what we know. And there's something, I chose this problem for a reason because there's something to be very careful about here. Okay, so we have 2 rates and 2 values here. Okay? That 3 centimeters per second is obviously a rate. Okay, because it says it's increasing at that by that rate, right? So we know the rate of change of length is 3. So we say dl dt equals 3. What about the rate of change of the width here? The word I want you to be very careful about here are these 2 words, increasing and decreasing. Because the length was increasing by 3 centimeters per second, my 3 should be positive in dl dt. But dw dt here needs to be negative 2. Be very careful. A lot of people miss that word when they're going through. dw dt is not 2. dw dt is negative 2. Right? The width is decreasing by 2 centimeters per second. Okay? The other 2 things that can go into our no column is that L equals 10 and W, what did I say, 6? W is 6. Those go into our no column. Our need column then, let's look at the question word. It says, what is the rate of change of the area? So what I need here is not the area. The area is 60. That's not a big deal. 10 times 6, okay? But what I need is the rate of change of the area. So I need dA dt. Okay? What I need is dA dt. Okay, so what I want to do now is I want to write an equation that when I do the derivative will give me dA dt. Well, that equation is obviously the area of a rectangle. That's an equation obviously you need to know. You should have known that a long time ago. The equation we have here is the area of a rectangle, which is length times width. Now, one thing I want you to be aware of here is both the length and the width are changing. So both L and W are variables here. What happens when we do the derivative of something times something? Right? What rule do we need to use? Well, we need to use the product rule. So this problem is going to have a product rule component to it. That's okay, we know the product rule. So let's just do the derivative of both sides. The derivative of A would simply be dA dt. No special rules needed there. But when I do length times width here, I need to make sure that I'm doing the product rule. The product rule says I do the derivative of the first times the second. The derivative of the first would be dL dt times the second, W, plus the first length times the derivative of the second, which would be dW dt. If you don't do a product rule here, you can't get this problem right. Now I'm just going to plug in and solve for dA dt and work this thing out and think about the units. So dA dt must equal dl dt. Well, I can find that over here is 3 times w, not dw dt, but w, 6, plus length, which is 10, right here, and dw dt, which is negative 2. Okay. Simplifying this out, I get 18 minus 20 equals negative 2. So interestingly enough here, even though my length is increasing by more than my width is, the overall area of this rectangle is getting smaller at this instant. Now, if I messed with those rates or messed with L and W, I could change this from a positive number to a negative number or vice versa. Okay, but I want to think about the units here. What would be the unit for the area of a rectangle? Well, in this case, it'd be centimeters squared, and our time unit is seconds. So we say dA dt equals negative 2 centimeters squared per second. So the area is actually decreasing by 2 square centimeters per second. Okay, that's it for today. Have a great Thanksgiving break, guys. You've earned it. Take good notes on this. Make sure you have these notes. I'll definitely check these ones on Monday. And we'll just have fun with these crazy problems. Talk to you guys later. 2 chains. Bye.